Okay, that's fine. Sorry, yeah, that's fine. I don't know if you can read these numbers. From the last, it's very hard. But I'm sorry about that. But we sent out those electronic copies, so you might be able to print it, or you can read on screen. On the screen, you can read it. It's not that bad. But all these numbers are from books. These are standard numbers. There are a couple of very good books. I can give you the references. There's one by Agarwal from Missouri State or something like that. He wrote a book on composite composite materials, actually. And there's another book by Barbito. Those are very standard books. These tables come from those books. So you might want to take a look if you are interested. So what you'll see here is typical properties of thermoset matrices. The difference between resin and matrix, what is it? Does anyone know? Resin is, before hardening, you refer to the material as resin. Before hardening. Once it hardens, you call it matrix. So in a composite, the hardened material is matrix. Before you made the composite, the flowy material is actually resin. Okay? So this is matrix properties. Different kinds of matrices, right? So polyester and iso whatever, BPA. So they have all these tensile modulus property here, tensile strength, compressive strength. They have compressive strength in some of them, and some they don't want to guarantee any compressive strength, which is fine. Shear strength, tensile elongation, flexural modulus, and so on. Let's look at these numbers just to get a feel for numbers. Okay, it's very important in civil engineering, structural engineering, to get a feel for numbers. So it's easier always to remember everything in relative terms. If somebody says, is steel stronger than aluminum, or maybe that's not a good comparison. Let's say, is steel stronger than Play-Doh or something like that. You can always say one is weaker, the other one is stronger. That you will remember. Whereas you may not be able to always, most of you remember probably, but you cannot remember the properties of other materials. You can always say, oh, wood is weaker than steel. You remember that. But what is the tensile strength of wood? Then I may be struggling to give you a number. That's how I see it. So if you see here, tensile modulus is a modulus of elasticity. GPA, what is the this one, tensile modulus of steel? We know that, right? It's 200. Is that right? 200, about 200 plus or minus, depending on the type of steel. So let's say 200. So this one here is 3.4. Can you see the difference? It's huge difference, right? So they are very, very, steel is very stiff material, very strong and also stiff material. Whereas matrix, not so stiff. The modulus is very, very low. That's what you might be able to remember. Oh yeah, matrix very, very weak in terms of modulus. What about tensile strength? Tensile strength is about 55, 75, 41, 20, 80, something like that. So in the range of 30 to 40, 50, something like that. So definitely it is much weaker than steel, right? Steel common grade is 415. Is it 415 nowadays? 415, Fe 415? Okay. 500 is common? Okay. So if you say 500, these are very, very weak in terms of tensile strength, right? So if it is 500, that's about 1/10 or even 15% of steel strength. That's matrix, by the way. Okay? Compressive strength, okay, not all are strong, but some couple of matrices have some compressive strength, which is reasonable. Shear strength is very low, obviously. Elongation, what kind of elongations do you expect in steel? Depends, mild steel, maybe 7-8%, maybe, right? or at least 6% at least. So here we have very low, 2%, 1.4. Epoxy may be slightly more, but everything else is low. So that's how I would remember. I say, okay, my flexural strength, 220, or about 200 MPa, which is not bad actually. It's much better than concrete. And then you have those numbers. Poisson's ratio is slightly higher than steel. So it's 0.38. That means it will expand laterally much more than steel. That's what it means. Does it make sense? You apply axial load, it will expand laterally more than the expansion of steel laterally. Does it make sense? So simple concepts. Okay, that's good. Similarly, you have for thermoplastic matrix, we have a few good things, a few bad things. Heat can alter. You can make it softer. You can make it like you can work with it when you heat it. So it has it's slightly more difficult to process and requires no refrigerated storage, slower processing time, more expensive. That's a big item. It's more expensive, so it's more common in aerospace industry. Unlimited shelf and part life. And the good thing about thermoplastic matrix is you can repair a composite made with thermoplastic matrix. All right. So they have a few different kinds. We can skip this. These are all available in market. You can always consult your supplier to use these different kinds of thermoplastic matrices. What is more important to me is these numbers. Numbers are important. If I am designing my composite, these are what I will use. Once again, modulus is very low. Tensile strength is not bad, but it's not high. So look at the tensile elongation, very large elongation. So if you have very large elongation, give me one or two applications where your large deformation or elongation will help. Absolutely. Anything that is subjected to impact or dynamic loads, if you are able to elongate, you will increase ductility, right? So any material with large elongation will absorb more energy. So that's a very good example. So and it's a very large elongation in terms of percentage, and then Poisson's ratio again 0.37, 0.38, it's same as other ones. Okay, so there are a couple of common concepts. So at high load rating is very important. So I'll ask you a question on this. So if I'm applying load at a certain rate and I get, let's say, some strength, okay? Now if I increase the load rate significantly, what happens to the strength? Does it increase or decrease? Increase or decrease? Are you sure? I thought it's the other way around. You increase the load rate, the strength will increase. Yes, what about steel? I think it's the same thing. You'll get slightly better properties at higher rate because the standards do give us a different set of properties under high load rating, high load rate. And those are always slightly higher than, I think, normal rate. You can check that. But I think it will give you larger strength. I think that it's the same thing here. High load rates or short duration loads Only thing is it becomes very rigid and brittle, so that's a problem, but so is concrete. Concrete is also brittle. Long duration loads, you can have better ductility and improve toughness. Generally speaking, 25 is a little bit low, but you will see in a composite, they are able, at least the fiber FRP bars, they are using about 50 to 60% volume fraction of fiber. So remaining is matrix. So this 25% is a little bit lower. Up to 50% is possible. So you can use 50% matrix and 50% fiber by volume in a composite. That's what happens. That means if you cut a section through one of these bars, this bar is high, actually high volume fraction. It's 65%. This is a different kind of bar. So you cut a section, you'll see 35 to 40% of this will be matrix, other 60% will be fiber. More the fiber, better or worse? For strength, it's always better. But the matrix will not wet the fiber in all over the entire surface, which is a problem. So if you want to have efficient load transfer, it's better to keep the fiber volume fraction not that high. Okay? All right. You should have sufficient fibers for stress consideration. That means the strength is always dictated by fiber in the fiber direction. And of course, you need proper viscosity for making sure the fiber is fully coated. So if you see a section through your composite, you will see something like this. You will have matrix here, fibers, and then remember on the surface you have sizing, which is a coupling agent. So that's a coupling agent which is helpful in improving the chemical bond between the matrix and the fiber. Almost all fibers will have some kind of coating or sizing. Okay? What about fibers? So continuous fibers are useful. Chopped fibers, whiskers are also, you can use them, but you need to add a little bit larger volume fraction. They also, the disadvantage of discontinuous fibers is it will have more creep deformation. Now, when you are designing a composite, you need to consider the fiber orientation. The strength is always in the direction of the fiber, tensile strength. And then fibers also have different shapes. They can have rounded shape, they can have square shape, and they can also have rectangular shape. But for most part, you will have round shapes. That is, the cross section will be circular in shape. Okay, and then they need to bond with the matrix. That's very, very important. So fiber orientation is also very important because all the strength and stiffness is fiber dominated. So fiber will dominate, the fiber properties will dominate the strength and other mechanical properties of the composite in the direction of the fiber. Okay, so you can have fiber only in one direction, like when you come and take a look, you can see all the fibers here. So sometimes you have fibers only in one direction. Reinforcing bars are generally, they have fiber only in one direction. Plates, such as this one here, actually this is, it has many layers, and these layers are, they have fiber in different directions. So each layer has one direction, so it gets strength in all directions. That's the whole point of this panel here. There are fabrics which will have fiber in two directions. So that's, I have fabric here, I have two directional mat here, one directional fiber here. So there are, depending on the application, you can have fiber in one direction, two directions, very rarely third direction, but you can have third direction also, fiber in the third direction, very rare. Through thickness, you probably won't provide any fiber. Does it make sense? So your fiber, like this one here, it will have fiber in this direction, fiber in this direction, but no fiber in this direction, vertical direction. So through thickness, fiber may not help much. So you can have multiple layers, just like I mentioned. You have one layer of this fiber in one direction, another layer in this direction, another layer in other direction. So you will get strength in all directions. Initially, I thought I will also present some material on ply mechanics. Ply mechanics can be used to determine the properties of the plate when you have different layers with different fiber orientation. It's pure mechanics, very simple, very uncomplicated mechanics. Then I thought maybe it's the 4-day, 5-day time period is not enough to present something like this, because this will take 2 sessions by itself. So I said I did not include that. But if you are doing any wraps, this will be useful. So if you are designing wraps, you may need to consider ply mechanics. I think this is the 5th time I'm mentioning this, or even 6th time. The strength and stiffness of the composite is based on the direction of fibers. Composites show elastic behavior. This is a very important concept. I think this is the first time I'm mentioning about the elastic behavior of composite. Very, very important. When you are applying tensile load, the stress-strain curve for composite is likely to be linear until failure. That's a big limitation. We'll talk about it. Very big limitation. We'll talk about this. Whereas in case of steel, you reach yield. After that, you have very large plateau, then you get your strain hardening. So you have yielding followed by strain hardening, and that gives us a lot of ductility. Whereas linear elastic behavior of composites is a problem, because you keep on loading, and at one point it will snap, break, fail suddenly. That's it. So you don't know when that point is coming, and therefore very large factors of safety are included in all these design guidance to somehow prevent this kind of brittle failure, which is because of linearly elastic material property. Does it make sense? We'll talk about it. It will be more clear when I present the stress strain curves. Okay. Just give me another 10 minutes. We'll close this after this. So once again, the matrix should have elongation greater than that of the fiber. Again, I'll highlight this tomorrow when I'm doing the micromechanics. Matrix should not shrink excessively. That's a problem. And then bond is very, very important. Use some kind of coupling agents if required. And this is very, very important. The last line is very important. It's not like a cookbook style design. You need to understand your mechanics reasonably well to design a composite. And it's highly unlikely that we as structural engineers will design the actual composite. We will use the properties given by the supplier, but we will not design and create the properties for the supplier. Okay? So it's not a cookbook style design. So some of the common fibers are, you must have heard all of these. Some of you mentioned this aramid fiber being very weak due to moisture, and then glass, carbon. There are other fancy fibers like boron, silicon carbide, and aluminum. Basalt is something I have worked with last 15 years. And one of the sponsors from Norway, they gave me lots of money to do research on basalt fiber, and I have a full-fledged specification just for basalt FRP reinforced concrete members. So I have developed that guidelines myself. So now let's look at this stress strain curve, or many of them. On the x-axis, okay, we have our first quiz right here. Let me quickly look at this before I give it to you. Yeah, I think we have covered all the questions, no problem. So you'll have no problem answering these questions, okay? So these are typical stress. You can give it to them, they'll pass it on. You can just leave it and they'll give it. Next. Okay. All right, so these are the typical stress strain curves for many common materials, okay? So on the x-axis, I don't know if you are able to see the bottom of this, but on the x-axis we have strain. Strain in x-axis as a percent. So we have 1%, 2%, 3%, 4%, 5% strain, okay? What about the y-axis? On the y-axis we have stress. Stress in Newton per millimeter square, which is MPa, right? Yeah. Newton per millimeter square, which is MPa. So we have 1000 here, 2000 MPa, 3000 MPa. Those of you who think in terms of KSI, kips per square inch, which is, I don't think any of you will be thinking in terms of KSI. But if you want to think in terms of KSI, we have a line that defines KSI as well. So this is 145, 290, 435. So what we have here is many different materials. We'll start with the ones that we know really well. Steel. Steel has bilinear, more or less, bilinear stress strain curve. Okay? And look at the numbers. Maybe this is about 400, which is what we expect, or even slightly less than 400. But anyway, this is the traditional steel reinforcement. And we have other fiber, nylon fiber, polypropylene fiber. Some of you probably use this in your FRC, fiber reinforced concrete. You use polypropylene fiber. Nylon, maybe not, but polypropylene is very common. Now, what about pre-stressing steel? Pre-stressing steel has very high tensile strength, right? I don't know if you remember or if you are exposed to that, but pre-stressing steel has about 1800 MPa. In fact, these days we can get 300 MPa, 300 KSI, 300 KSI pre-stressing steel. So that 300 grade steel is somewhere here. So it's greater than 2000, which will be 2100, let's say. 2100 MPa, very strong material, right? Now, there are many different fibers. Carbon fiber is shown here. It's a straight line all the way up to here. But at this point, it has no yielding. Very important. If you want to remember anything from today's lectures, remember this. All these fibers have linear stress strain curve up to failure. And that's going to be a limiting factor for us. I'll explain that later. Some of these other fibers, carbon HS, HS stands for high stiffness. We'll talk about it in a minute or maybe tomorrow. But carbon fiber is generally considered to be very strong fiber. So when something is really good,